Introduction. The end is near. The terrestrial archives of the late 20th century are filled with strange incongruities. For example, in the news sheets printed on vegetable pulp from their years 1970 to 1979, in their base 10 system, roughly corresponding to the years 4F26F to 4F272 in our calendar, there are many humorously intended drawings portraying old bearded men wearing sandals and long robes, carrying signs that say, in effect, the end is near. The sandals and robes in these cartoons were meant in the context of that time and place to convey the sense that such men, called prophets, were anarchistic remnants of an ancient and obsolete tradition, eccentric but harmless. The sophisticated urbanites of that time prided themselves on a scientific, enlightened worldview that rejected catastrophic or apocalyptic predictions, especially those with religious or philosophical overtones. Science was then clearly in the public favor. Several expeditions had recently been successfully dispatched to their moon, a class B7P-11 locked single satellite. In bizarre counterpoint to their tone of gentle mockery of catastrophe, one of the most widely reported news topics of the decade was the development of a truly apocalyptic computer model of the terrestrial economy. Computers were then in a state of extreme rapid development, driven largely by international military and space competition, with annual dramatic increases in computer size and speed. Many problems which had been computationally intractable just a few years earlier, such as long-range weather predictions, nuclear reaction, network analysis, and planet-wide economic modeling, were then under study for the first time. Thus, the same news sheets that mocked the sandaled prophets also virulently reported the work of economists and from a prominent university, the Massachusetts Institute for Technology. These savants proposed to show that the resources of their planet must inevitably be exhausted within a few tens of years. No matter what assumptions regarding the standards of living, energy consumption, recycling, etc., were inserted into their model, the result was always global famine and economic chaos within a single human lifetime. These calculations astonishingly made no allowance for space technology and the access it provides to the new sources of energy and materials. Their message was unambiguously, the end is near. From the Sociological and Economic Studies of Terrestrial Archive Materials, Overview Unit 2, 4F3A1. The age of exploration in which we live commenced, or so we are told, about the year 1419 with the first true European voyage of exploration, a Portuguese expedition to the Madeira Islands, fostered by new navigation and shipbuilding technologies introduced by Prince Henry, the Navigator of Portugal. European sailors opened up first Africa, then India, and then the Americas, and East Asia to the European economic, religious, political, and military influence. A small percentage of the planet's population, principally the residents of England, Spain, France, and Portugal, came to exercise dominion over most of Earth. Smaller or less vigorous exploring nations such as the Netherlands, Italy, Belgium, Germany, and Sweden founded colonies but soon lost them or found out they'd been hemmed in by the European maritime powers. English became the language of the United States, Canada, New Zealand, and Australia, and the unifying tongue of India and many African nations. French became the common language of West Africa, and Spanish and Portuguese filled the Americas from Rio Grande to the Antarctic. This is our familiar textbook history. In many ways, the European domination of the world seems to have been inevitable. The trade goods, profits, and cultural stimulation of the age of exploration fueled the economic and social revitalization of Europe. Simultaneously, the sudden imposition of European ideas and religion caused a devastating cultural earthquake in conquered lands. Most of the world quickly became dominated by European culture and language. But it almost did not happen. During the Ming Dynasty, a passion for exploration swept China. Starting in 1403, great treasure fleets were dispatched to map the coast of East Asia and establish trade relations. The fleets headed westward, opening the coasts of India and the Arabia to the Chinese trade. Later Ming expeditions progressed down the east coast of Africa, rounded the Cape of Good Hope, and headed north. They sailed past the Congo to the Great Bulge of West Africa, reaching the very doorstep of Europe about the time that young Henry the Navigator convened his great assembly of pilots, map makers, shipwrights, astronomers, and instrument makers at Sagres in 1421. But just before the fleet were due to break European waters, establish trade with Portugal and Spain, and discover the entrance to the Mediterranean world of China into the but just before the fleets were due to break into European waters, establish trade with Portugal and Spain, and discover the entrance to the Mediterranean, word of the Chinese emperor's death reached the fleet. The court eunuchs, alarmed the waste of resources on voyages, recalled the fleet and ordered an end to exploration. There was dissent. The eunuchs ordered the treasure fleets beached and burned. There was still dissent. The eunuchs ordered the plans and records of the expeditions collected and be burned. By 1433, China had again cut itself off from the rest of the world. China undoubtedly could have become the dominant power throughout the world if it had only preserved its program of exploration and trade for a few more years. The sole language of modern world would have become Mandarin Chinese. It may still again. Similar choices face us in the closing days of the 20th century. We have sent forth our expeditionary fleets to map the far side of the moon, never before seen by human eyes, to pierce the clouds of Venus and see its hellish surface, to land on Mars and seek signs of life on its surface, to sail by the giant planets Jupiter, Saturn, Uranus, and Neptune, and their retinues of satellites. They've got a lot of satellites. To explore the byways of the archipelagos of asteroids. 12 men from the Earth have walked on the moon. News of the fabulous wealth of energy and materials within our solar system has begun to trickle back to Earth. But the Emperor is dead. There is no leadership. The dream must die. At the height of the Apollo program, the National Aeronautics and Space Administration cancelled production of the Saturn I and V boosters. With them, the human race lost its ability to send astronauts to the moon and beyond. Then began the enormously expensive diversion of the Space Shuttle program. An incomparably less capable booster, which we cannot even dream of flights to the moon. The last 3 flight-ready Saturn V boosters, already built and paid for, were laid out as lawn ornaments at Cape Canaveral, Marshall Space Flight Center, and Johnson Space Center, to rust into ruin and to serve as testimony to the futility of that dream. Only governments can afford to spend $250 million each for the equivalent of plastic flamingos. The tools and dies for building the Saturn V were collected and sold as scrap metal for pennies on the pound. A $20 billion investment in the future was melted into dross. The plans and blueprints and operating instructions for the Apollo hardware were declared surplus. One set of Saturn V plans was donated to a Boy Scout paper drive. The last apparently complete set of plans was sent to the Federal Record Archives in Atlanta. My attempts to find them several years ago met with no success. The plans have evidently been lost. The fleet has been destroyed. The plans are gone. The Enochs have won the day. Despite the rarity of visionary leadership in recent years, Earth has been blessed with a host of true visionaries. Since the early 1900s, certain engineers, scientists, and writers of futuristic fiction have foreseen human presence in space that is sustained not by political posturing, but by economic and practical self-sufficiency. The idea that technology could make the heavens accessible and useful to us dates from the beginning of this century, from the pioneering and independent work of Kostan Chuskovich in Tsarist Russia, Robert Goddard in the United States, Henry Oberth in Germany. We shall see how writers of science, engineering, and science fiction, such as Arthur C. Clarke, Olaf Stapleton, and J.D. Bernard, sketched out ways to make human explorers and colonists evidently self-sufficient in space. But these visions were not shared by political leaders. Even after the space age had arrived, indeed even in the Apollo exploration of the moon, the concept of using lunar materials was avoided because of the engineering conservatism and short-sightedness. The lunar landings were regarded as a short-term, dead-end political goal, not a long-term commitment to move into space on firm economic footing. The United States and Soviet Union undertook the exploration of space as part of a fierce rivalry of the Cold War. To hone technologies of potential military value while demonstrating their competence in a peaceful but technically challenging competition. It was that bitter rivalry that led us to lift our gaze to space. But what we have seen has transfigured us. The space age has opened our eyes both to the rare beauty and vulnerability of Earth, and to the incomparable richness and variety of our cosmic surroundings. Seeking to score points against one another in the eyes of global opinion, the American and Soviet exploration programs enlisted thousands of scientists and engineers whose efforts served to make space into a real place, ever more accessible to all humankind. They have found from the study of other planets new insight into the nature and governing laws of worlds. Many of these insights have been brought home to Earth to inform us of the nature of our world, instruct us in its governing laws, and to guide us in designing public policy so as to preserve our beautiful Earth. Venturing forth into space, we expected to find a harsh, deadly vacuum, a quarantine notice for the human race. Instead, we have found a lively, rich understanding of the unity and lawfulness of creation, within which the diversity and complexity of local materials and events fall naturally into place. The deadly vacuum is still there, but now we know vastly more about the laws of living in space and about the resources available to sustain life on Earth. These resources, in fact, greatly surpass those available to us on the Earth's surface. The tired old myths of limited resources and finite living space available to humankind cannot be sustained in the face of discoveries now pouring in daily about our solar system. Indeed, the global expansion of European technology and civilization, brought about by the terrestrial age of exploration, is but pale foreshadowing of the opportunities before us as humans move out into space. Sadly, the domination of space activities by governments has caused the price of space travel to remain very high. Indeed, with the space shuttle, the cost of access to space actually rose further, reaching $10,000 per kilogram of payload carried into orbit. Governments do not need to show a profit, and they have strong institutional incentives to keep costs, and therefore budgets, as high as possible. The tradition of high costs arising out of centralized government control has generally generated another tried new myth that space travel must be very expensive. But this is most certainly not true. The cost of launching payloads from Earth into space can be brought down dramatically by using the most elementary principles of free enterprise, starting with free and open competition. Several launch vehicles now in development could promise launch costs under $1,000 per kilogram at the very beginning of the competitive era. The ultimate result in competition will be that the cost of transportation into space will be only a few times higher than the cost of fuel. The actual cost of fuel to carry a payload into space is astonishingly far lower than present launch costs, about $3 per kilogram of payload placed in orbit by a rocket fueled with liquid hydrogen and liquid oxygen. In fact, at present price of electric power, the energy needed to put a kilogram of payload into orbit costs only 50 cents per kilogram. A 75 kilogram adult would at this price pay $37.50 for the energy to launch themselves into space, allowing for lifting the vehicle as well as the passengers, paying salaries and setting aside a decent profit margin. A ticket to orbit could go for as little as $500. Once in orbit, you are precisely halfway to having enough energy to escape from Earth. For twice as much energy and twice as the expense, you could escape from Earth entirely. But if you're going to a remote destination, such as the asteroid belt, the cost of your transportation would be dominated by the cost of launching the food, air, and propellant you would need to get to your destination. Of course, if the fuel and life support materials did not have to be lifted from Earth, then you could go just about anywhere in the solar system for a few $1,000s. Once in space, we should probably use the resources of other solar system bodies simply to provide the consumable propellants and life support materials to reduce the costs and increase the performance of space missions. The first body to be exploited will probably be the nearest body to us in space, our Moon. The Moon is unfortunately a barren body devoid of atmosphere and liquid water. Studies of the lunar surface by American and Soviet spacecraft and by Earth-based telescopes have revealed a slag-like composition of the lunar crust, rich in silicates and oxides but very poor in both volatile materials, hydrogen, carbon, nitrogen, and so on, and free metals, as discussed in Chapter 3. Despite its unattractive aspects, the Moon presents several opportunities for resource use. At first, mostly to defray the expense of expeditions to explore its surface. In Chapter 4, we should discuss how oxygen extracted from the lunar rocks or lunar polar ice, if present. Oh, it is present, if present. It has been found since this has been written. It can be used for life support and rocket propellant. Polar ice also would provide hydrogen for rocket fuel and industrial purposes. Lunar dirt can easily be used as radiation shielding, and metals can be made as a byproduct of oxygen production. The principal market for these products would be on the Moon itself. Export of propellants in support of large near-Earth space activities may conceivably be economical. But the Moon is by no means the only accessible body for resource use. As discussed in Chapter 5, Spacewatch and other astronomical search programs have found that the Earth is embedded in an immense swarm of comets, asteroids that threaten us with collision and global mass destruction. Thousands of kilometer-sized bodies cross the Earth's orbit. Many recently discovered asteroids that follow orbits similar to the Earth's have very high probabilities of impact. There are at this moment at least 400 Earth-crossing asteroids larger than a kilometer in diameter that will certainly collide with the Earth at some point. The only uncertainty is when these devastating impacts will occur. The very asteroids that present the greatest danger to us are also the most accessible bodies in the solar system. Many of the most dangerous are actually easier to reach and land on than the Moon. Protecting the Earth from catastrophic impact of such bodies can be achieved using known technology, as he discussed in his book Reign of Iron and Ice. But many space propulsion systems developed to give us access to these bodies for defense reasons also give us access to their resources. These nearby bodies contain a wide range of valuable materials. Many are as rich in water, both as ice and water-bearing materials, Natural stainless steel, containing many valuable metals such as nickel, cobalt, and the platinum metals, make up 10% to 99% of the total mass of asteroids. In chapters 5 and 8, we explore ways in which fundamentally important industrial materials such as water and metals can be extracted automatically from near-Earth asteroids and extinct comets. These raw materials can be used to make propellants, life support materials, air, water, and nutrients, and structural metals in quantities large enough to make in-space operations profitable and self-sustaining. Among the commodities that might be returned for use on Earth are precious and strategic materials and cheap, clean, abundant energy. As an added benefit, industrial use of these bodies protects human civilization on Earth from the danger of destruction by their impact. But the resources of the Moon and asteroids are of no interest unless we have economical access to them. As discussed in chapters 6 and 7, access means that we have technically feasible, economically competitive transport systems with low propulsion energy requirements and opportunities for repeated round trips. Taking advantage of propellants made on the Moon or of asteroids greatly extends the list of attractive and affordable missions to Mars, the asteroid belt, and elsewhere by dramatically lowering Earth launch costs. In Chapter 7, we see how repeated round-trip missions are selected near-Earth asteroids can pay off by returning 100 times the mass originally launched from Earth. Logistics considerations make the Moon a very attractive base of operations. As ice is abundant in the lunar polar regions, export of materials and propellants from the Moon is of marginal attractiveness because of the Moon's substantial gravity. One of the few commodities that we might hope to import to Earth from space profitably is energy. We discuss in Chapter 8 how importation of energy from space can relieve our planet of the burden of fossil fuel combustion and nuclear waste disposal. The 1977 proposal to launch solar power satellites into high orbitals to transmit electrical power to Earth gains considerable benefit from these lunar or asteroid materials. We could build the low-tech parts of these power satellites, wires, cables, propellants, beams, and fixtures, and maybe even solar cells in space because launch costs from the Moon or nearby asteroids could be lowered to less than the costs from the more massive Earth. Alternatively, arrays of solar cells may be made on the Moon out of lunar materials, and only the power exported. The lunar surface also contains the light isotope helium-3, which implanted in the surface by solar winds. Helium-3 and the heavy hydrogen, deuterium, can in principle be used as the fuel of huge fusion reactors to generate cheap, clean electricity. Finally, if solar panel satellites are built in high orbits around the Earth, by far the most attractive source of raw materials to build them may be small, nearby asteroids with negligible gravity. The only other bodies besides the Moon and nearby asteroids and comets are reasonably accessible from Earth are Mars and its two natural satellites, Phobos and Deimos. In the survey of Mars in Chapter 9, we see that the red planet has a bright, extensive polar caps of ice and solid carbon dioxide. The surface is widely and deeply scored by the valleys of ancient rivers comparable in flow to the Amazon. Certain Martian surface features have been interpreted as evidence of ancient ocean beds and widespread glaciation. The craters made by large cometary and asteroidal impacts give strong evidence of a deep layer of permafrost and ground ice over most of the planetary surface. Water is extremely attractive as a source of both propellants and life support materials. Polar ice, snow, and permafrost are widespread, and water-bearing materials are probably universal on the Martian surface. All are testimony to a wetter, more benign past. Expeditions are made far easier and cheaper by use of rocket propellants made on the surface of Mars. In Chapter 10, we explore how propellants can be readily made from carbon dioxide in the atmosphere, from water, and from native materials. Even unpiloted sample return missions would benefit greatly from the automated local production of propellants. The frozen present of Mars conceals a warmer, wetter past and allows a lively future. Phemios and Deimos are strange and wonderful bodies. Both of these too small, irregular moons are generally similar to asteroids, but they are gravitationally bound to Mars. If they are similar to the Carboniferous chondrite meteorites, they would be very attractive refueling stops in the Mars system, providing propellant for landing on Mars and returning from the Mars system to Earth. The attractiveness of asteroids as resources is now obvious, but we have so far concentrated exclusively on the small minority of asteroids that have orbits bringing them close to Earth. What of the vast majority of asteroids which orbit the Sun far beyond the orbit of Mars in the asteroid belt? As discussed in Chapter 12, many of the near-Earth asteroids that are more accessible than the Moon pursue eccentric orbits that approach the Sun close enough to graze or cross Earth's orbit, and then retreat as far away as the heart of the asteroid belt. Any equipment installed on these bodies will get a free trip to the belt every few years as the asteroid pursues its orbit about the Sun. It's relatively easy to ride a near-Earth asteroid out from Earth to the belt, and there to transfer any of the tens of thousands of large belt asteroids. The wealth of materials available in these asteroids discovered in the study of meteorites staggers the imagination. There is enough raw material in the asteroids to support a population much larger than that of the Earth. We have so far concentrated principally on the use of space resources to support future activities in space. In doing so, we have found that the energy resources of the inner solar system, including both the solar power and fusion of lunar helium-3 with terrestrial deuterium, are sufficient to meet the foreseeable energy needs of the Earth for the indefinite future. Both power for activities in the belt and for propulsion of spacecraft is harder to find. The intensity of sunlight is about 10 times lower in the belt than in the inner solar system, making all solar power schemes less attractive. Extraction of helium-3 from the surfaces of asteroid is not likely to compare with that of the Moon. But the asteroids of the Jovian planets contain astronomical amounts and high concentrations of both helium-3 and deuterium. The massive gravity worlds of Jupiter and Saturn render them very unattractive sources of materials, but Uranus and Neptune have low enough escape velocities to be amenable to the export of helium-3. The availability of this energy source allows infinite future, which we'll explore in Chapter 13. The implications of abundant, cheap, clean energy for Earth are profound. We're all aware that the Earth is in the coming third millennium faces a variety of urgent environmental problems, and in Chapter 14 we consider new solutions. We must keep in mind that planet Earth's ebbing supply of fossil fuels, emerging environmental hazards such as global warming, acid rain, and ozone depletion caused by the combustion of hydrocarbons and coal, and the uncertain prospects for safe disposal of radioactive waste from nuclear power plants. These discouraging factors combine to compel a search for cheaper and environmentally safer energy resources. Solar power and fusion power are the two leading contenders. The exploration of space technology offers the most attractive solution to the energy problem now visible. We should also anticipate having powerful new technologies at our disposal for our use in space. Drawn from fields as diverse as plasma physics, computer science, and genetic engineering. New tools from these fields will greatly diminish the cost of doing work that needs to be done. The expansion of human civilization into space is feasible because of the availability of vast asteroidal and planetary resources. But these resources will be ours only if we choose to pursue them. Chapter 15 lays out the choice before us. We may choose either to retreat into a stagnant, shrinking future and play a zero-sum game on an exhausted planet, or to expand into a vast new arena of activity, rich in material wealth and vibrant with energy, which will allow us both the freedom to escape the cradle and the resources to keep our home planet alive and well.